AB 2018 AP exam question number 4. Question answers: the height of a tree at time t is given by a twice differentiable function. That's important. They're giving that to us for a reason. Okay. It says function h, where h of t is measured in meters. See, h of t right here is measured in meters, and t is measured in years. The selected values of h of t are given in the table above. So it basically means that they measured this tree when it was 2 years old and found it to be 1.5 meters. Then at 3 years old, 2 meters, 5 years old, 6 meters, so forth. Okay, it doesn't matter how it grew in between there. It's just saying is that these are the only specific measurements they took. Okay, let's look at part A and see what's going on here. It says use the data in the table to estimate h prime of 6. Now, what is h prime of 6? H prime would be the slope, or it's the derivative of h of t. H prime is the derivative of h. So it wants to know the slope of h of t, the slope of this data here at t equals 6. Okay? And use the correct units, interpret the meaning of h prime of 6 in the context of the problem. So what I did here, I plotted the points, and these are the 6 points that are given to us right here. Okay, so you had time 2 years, it was 1.5 meters, 3 years, it was 2 meters, just plotting this data. And the time is usually or always going to be the independent variable. And then just for the fun, I just connect the segments between those times. Okay, now we don't know how this grew over this time period, but we do know that it grew from here to here. So the simplest way to look at it is to just draw segments between there. And then what we want to know is, we want to know what the slope is, h prime at t equals 6. So here's t equals 6. We want to know the slope in here. So if we just took the slope of the segment here, because that's the only thing we could figure out between these 2 points, and if we do that, we could find what the h prime of 6 would be. Now be careful here. So here we have the change in slope is change in y over change in x, but we're dealing with a function, so this is going to be change of meters. Okay, change in y over change in x is just very generic, and this particular thing, the slope is going to be change in meters over change in x, which would be change in years. And so here is h prime. So h prime. So we should write this out. H prime of 6 is going to be h of 7. H of 7, h of 7 minus h of 5. It's just the slope between these 2 points here. And and then it would be the time would be 11 minus 6. Excuse me, 7 minus 5. So here's h of 7 minus h of 5. That's the change in h over change in time, which is 11 minus 6 over 7 minus 5, which is 5.5 meters per year. That's its rate. And another way of looking at it, over this time period from 5 to 7, it grew 5 feet. And it was a 2-year period, so it basically grew 5 feet in 2 years. It grew 2.5 feet per year, or 2.5 meters per year. And now we always have to answer your question, so let's write our answer out. So h prime of 6 is the rate. Just take the question and reword it. It's the rate at which the height of the tree is changing in meters per year, correct units at. You always have to say when. It's not all the way through here. It's at this time t equals 6. Now, next question, I want to go through a theorem which is very important before we start to answer part B. And this is a very important theorem, and I think if you can visualize the theorem, you'll learn to understand it. This is how I remember formulas. I can visualize this theorem here. So this is the mean value theorem for derivatives, it's called. And here we have some function that is continuous and differentiable. And if I took some interval, now if you notice, no matter what I'm just changing the interval, A is changing, or I could change B, so the interval is changing. And if you draw a secant on this interval, so secant, remember, just like a secant in a circle goes through the circle, or a secant would go through the 2 points here on the curve. That would be a secant line. This theorem says that some place on this interval between A and B, there's some point C where if I draw and hit the tangent, hit the curve there and draw a tangent, someplace there's some c where the tangent is parallel to the secant. So the mean value theorem for derivatives, slopes, so it's talking about the slope of the tangent is equal to the slope of the secant. And we notice now, no matter how I move this, you can see that these two lines are parallel. The blue line and the red line are parallel. So that's just saying that someplace in there, the slope of the tangent, there is a place where the tangent to the curve at some c is parallel to that secant. So here's the equation itself. So the important thing is mean value theorem for the function must be continuous, no breaks, differentiable. It must be a nice and smooth curve. And then it says the slope, see, slope of the tangent here is equal to the slope of the secant. That's what the theorem states. So what is the slope of the tangent? It's at some point c, so that's f prime of c. And that's equal to the slope of the secant, which is the slope of a line between 2 points, which would be change in y, which is f of b minus f of a over b minus a. And that's the mean value theorem for derivatives. Slope of a tangent is equal to the slope of a secant, but it must be a continuous differentiable curve. So let's see how we apply this here. So this is part B now. It says explain why there must be at least one point, at least one time t on the interval from 2 to 10. So someplace in here there must be one point such that the slope h prime of t is equal to 2. So they're saying, is there some place in here where the slope is equal to 2? All right. So here's the mean value theorem. Remember, the mean value theorem says the slope of a tangent. This is the slope of the tangent. It means someplace there must be some slope. If I pick 2 points here, there needs to be it says that it should be a slope of 2 because this is a twice differentiable function. Therefore, it is also continuous. And so here's the mean value theorem. So there's what I wrote, and I'm applying it here to this problem here. So the slope of a tangent, which is h prime, see h prime of c, some c where the slope is going to be 2 is going to be equal to the slope of the secant between these 2 points. So the way to do this is just look at this data here, and let's just see if you can come up with a slope of 2. In other words, if I pick the first 2 points, this would be my change of h, which would be 0.5 over 1, so that's the slope of 0.5. If I take these 2 points here, this is a slope. The change in h is 4, change in time is 2, so 4 over 2 is 2. That's the slope of 2. So you just got to look through the data and just keep playing with it. If you looked over here, this would be 15 minus 11 is 4, so that's the change in h is 4, but here the change in time is 3, so 4/3, this would be 4/3, so this is not 2. So it has to be these, it could be other points, but it is these 2 points right here. Okay? So now just show what I'm doing here. So h of 3, you need to show what you picked. So h of 5, which is 6, h of 3 is 2. So h of 5 is 6, h of 3 is 2, over 5 minus 3, which is the change in time, is 6 over 4, or 5, which is 2. And that's all I had to do there. So you're using the mean value theorem. And here's the segment right here. I'm showing the segment which is using these 2 points where the slope is 2. And now just write your answer. It says h is differentiable. Since it's differentiable, therefore it's continuous. Then by the mean value theorem. And you always have to state the region. It's someplace between 3 and 5. We don't know exactly where, but it is someplace between 3 and 5. There's some point for t between 3 and 5 where h prime of c is equal to 2. Another theorem, it says the mean value theorem for integrals now, and I want to do this because this has to do with the next part. And again, if you can visualize this, it makes sort of sense. If I want to find the area under this curve, this yellow region here, the mean value theorem for integrals, now remember, integrals has to do with definite integrals, which is an area. Okay, that's a way of remembering it. And so it says that the area under this curve, the yellow region, can be approximated by some rectangle. So if I take the same base, here the curve goes from 1 to 3 in this case. In general, it goes from A to B, but in this case, it goes from 1 to 3. It's saying some place if I move the height of this thing along here and form this rectangle, someplace the area under the curve, the yellow, is going to equal to the area under the rectangle, which is like this dark shaded region here. So this region in here is an intersection of the yellow and the black here. So the way to do that is just kind of approximate where these two pieces are about the same size. Because this is under the rectangle, but it's not under the curve. This is under the curve, but not under the rectangle. So if I could take this piece and chop it off and squeeze it in here, then I would have the area under the curve. So that's what the mean value theorem states. And this place is some place where it hits the curve here. This is where C is, okay? This would be f of C. So how do I find the area of the rectangle? Well, let's just see. Here's the mean value theorem. The curve must be continuous on the interval. And it basically says that the area of a rectangle, the area of some rectangle, is equal to the area under the curve here, the yellow region. And the area of the rectangle is just the base, which in this case, in general, it's b minus a. And then the height would be f of c, some f of c. C is some point in here where it hits the curve. That's where we get f of c. That's the height of this rectangle. So that's b minus a, base times height, f of c, is equal to the definite integral under the curve from a to b of f of x dx. Now we can take that one step further, and this is where we get the average value formula from. The average value, this is considered the average value of f. So if I want f average, this is the same as f average. I just divide by b minus a. What that basically is saying here is when I find this rectangle that has the same area, this height right here is the average height of this function. Now, if you look at the height of this function from 1 to 3, the height looks like it goes from 1 over here, and at 3, it's up here about 9. Okay? So the height, obviously, the average height must be between 1, the lowest value here, 1 and 9. And it looks like the average height is someplace around 4.5 or so. So that would be the average height. And the area under this curve would be approximately, the base is 2. And if the average height is around 4 or 4.5, the area under this curve would be 2 times 4.5, which is about 9. So the area under the curve is approximately about 9. That's the mean value theorem for integrals. So now let's see how we're going to apply this. So this part of the question says, use a trapezoid sum with 4 subintervals indicated by the data in the table to approximate the average height. See, we want the average height of the tree over the time interval from 2 to 10 years. So here's from 2 to 10 years. Now, something you should take note of. The average height. Notice this tree, the height starts at 1.5 and it ends up at 15 here. So the average height has to be someplace between 1.5 and 15. So if you get an answer of 60 or 70 or 80 or something like that, you should be, well, even 20, you got to know that you're wrong, okay? Because it's got to be between here and here. So they want us to use the trapezoidal sum with 4 subintervals. Now this always works out nicely. You see the data is plotted, and I have the 5 points, so the intervals would be, here's one interval, just go from the points, and I'm just breaking this up into 4 partitions. So these are 4 subintervals, all right? And then it wants us to use a trapezoidal sum. So the question now is, how do I find a trapezoid? So here, wrong part again. There's the area of a trapezoid in general. Area of a trapezoid is the height times the average of the bases. Now don't get confused here, but these trapezoids, let's look at the big one, it's easier to see. The bases are the parallel sides. So these 2 sides are the parallel sides of this trapezoid. So these are the bases, and then the height would be down here. So if I want to find the area of this trapezoid here, it would be the height, this value right here, times the average of the 2 bases. So let's look at these areas here and just see. So I broke it up and they're colored here. So you can see now that all the heights are on here. See, the 1.5 is the height here. Excuse me, the base here. 2 is the base. 6 is the base. 6 is this base. 11 is the next one. 15 is the next one. The heights are the change. So this one goes from 2 to 3. So its height is 1. This one goes from 3 to 5, so its height is 2. This one goes from 5 to 7, so its height is 2. And this one goes from 7 to 10, so its height is 3. So if I want to find the area, if I want to find the area of this trapezoid right here, it would be the height, which is 3, times the average of the two bases, meaning add these two bases and divide it by 2. So let's look at the area here. So I just wrote it out now. So the area, and I did it color-coded so you can see it. Here's the first height, and there's the two average of the two bases, plus just adding up these four trapezoids. So here's the height, average of the two bases are 2 and 6, and then average of these bases are 6 and 11 times the height, which is 2. The height is 3, average of those bases, and then you just have to go through and do the arithmetic. Be careful with the arithmetic. By the way, you probably could leave the answer. I mean, that is your answer technically. Okay, you're showing your work. This would be your answer, but it is not cleaned up. I would think if you stress for time, you might get full credit if you left that for an answer. So now let's see what does the mean value theorem have to do. So what we did is we found the area under these regions, okay? But we want the average height. So remember, this is the mean value theorem now, but I'm applying it. It's the area under the rectangle equals the area under the curve, okay? And so the area of the rectangle would be b minus a times h of c. This would be the average height, and it would be equal to the area under the curve. And the way we're finding the area under this curve, because we don't have the function itself, we just have these data points, we're using trapezoidal sum. So we're doing this part by the trapezoidal sum right here. So this part we have, so the average value now, so here's h average, this is h average, I just take this and divide by b minus a, so 1 over b minus a times this integral. And this integral we just approximated using trapezoids. So that would be area of our trapezoids. And this interval went from 10 to 2. Okay, right here from 10 to 2. So this is 1 over 8, and this is the area of the trapezoids. And you get, this is just 263 over 32. Now what some people, they forget a lot of times is this 1/8. And that's how, when you estimate this answer, remember the answer's got to be between 1.5 and 15. And if you didn't do that, if you left it like this, it would be about, 60 or 70 or so, somewhere in there. Okay? And so you'd know that was absolutely wrong. Now, what I did here is, here's our answer. So the average height of the tree over the time, you always put the time interval over this time from 2 to 10 is, just leave it as 263 over 32. I did this calculation just as approximation to see if you did divide these two numbers, you'd see that 3 goes into 26. It goes in about 8 or 9 times. So it is 8.22. So the average height, 8.22, is between 1.5 and 15. See here, the average height is right about here, 8.22. So the average height of this graph here, it's saying is right about in there, which is about 8.22. The last question is changing things here a little bit. It says the height of the tree in meters can also be modeled. It's being modeled now. The height of this tree is being modeled by this function g. So g is the height of the tree, and it's given by 100x over 1 plus x, where x is the diameter of the base of the tree in meters. In other words, when the base of the tree is 1 meter, that means the height of the tree would be 100 times 1 would be 100 over 1 plus 1 is 2. So the height of the tree would be 50. Right? If this was a 3, so then the height of the tree would be, if the diameter of the base was 3 meters, then this would be 4, this would be 300, so the height of the tree would be 75 meters. That's all the same. Now it says when the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate. In other words, this tree is growing, and it's growing, the diameter of the base is growing at a rate of 1.03 meters per year. And then wants to know, according to this model, what is the rate of change of the height of the tree with respect to time in meters per year? Excuse me, at the time when the tree is 50 meters tall. So here's our model. Now you have to be a little careful here because what we need to know is, well, we need to know a couple of things here, but we want to know the rate of change of the height with respect to time. So we want to know dg dt. Okay, so we have to differentiate this with respect to time. And in doing that, we'd have to use the quotient rule. And you got to, so here's a quotient. I just kind of, I like to do it sometimes in terms of denominator numerator, d for denominator and n for numerator. So the quotient rule, and the way I do it, because of this negative sign, a lot of people screw it up. It's the denominator squared, and then it's the denominator times the derivative of the numerator. So if you do it that way, you don't mess up. Denominator squared, denominator. Derivative of the numerator minus numerator times the derivative of the denominator. That's the quotient rule. So I always start it that way so I don't mess it up. Okay, so let's take the derivative of this. Now remember, we're differentiating with respect to t. So here we have the denominator squared. There's the denominator squared. Then we have the denominator times the derivative of the numerator. Now we're differentiating with respect to t, so the derivative of this is going to be 100 times the derivative of x with respect to t. And then minus the numerator, 100x, times the derivative of the denominator with respect to t. So the derivative of 1 is 0. The derivative of x with respect to t is the x dt. So there's your derivative using the quotient rule. Now I need to plug in the thing. So what I want to know now is dg dt. So I have to know x, and I have to know dx dt. Well, dx dt we already know. That's 0.3. That's given 0.03. That's given to us. So we know that, but we don't know. So we know 0.03. We don't know what x is. But we do know it says when the height of the tree is 50. So if we have this equation, when the height's 50, we can find x. So I just did that calculation over here. So when the height is 50, if you just multiply 50 times, multiplied by both sides by 1 plus x, I get 50 plus 50x equals 100x. And then bring the 50x over here, I get 50x equals 50, or x equals 1. So when the height of the tree is 50, the diameter of the base is 1. So now I know the diameter of the base is 1. So this is 1 plus 1, 2 times this 100 is 200. That's 0.03 minus the base is 1. So 100 times 1 is 100 times 0.03. And that's over base is 1, 1 plus 1, which is 2 squared root of 4. So if you just do this arithmetic right here, this becomes 3/4, and that's meters. Remember the height in terms of time, meters per year. So that means the height of the tree is growing at a rate of 3 meters per year at that time. So rate of change of the height of the tree when the tree is 50 meters tall is 0.75 meters per year. Now what I did is just to kind of give you a little feeling for what this might look like. It's hard to visualize this kind of a thing here, but here I'm just kind of showing you. By the way, this is not drawn to scale, because if the height of the tree was 50 meters and the base was 1 meter, this is not 50, the height is not 50 times, but just to give you a little feeling for it, because I can't fit it on a page here, or it'd be so thin you couldn't tell. But here's what's going to happen. It's going to grow. You see, it's growing, but the height is growing faster than the base is widening. Okay, and then here's all the information here. I just redid this. When the height is 50 meters, the base is increasing at a rate of 0.03 meters per year. They gave us that. And since we have the height equation given by this, and when we differentiated it, we get the rate of change of height with respect to time, we calculated that the base was 1 and the rate of change of height was 0.75 meters. So basically, even though this isn't exactly true, because this is changing continuously, but this sort of means that during the year when the height was 50 meters, the height changed from 50 to 50.75. It grew 0.75 meters during that year. And the diameter of the base changed from 1 meter, it was 1 meter, it grew to 1.03 meters. So that's what this is saying, basically. So over that time period, the base changed from 1 to 1.03 meters. The height changed from 50 to 50.75 meters. just to give you a little feeling for what's going on here. So let's look at the answers now. So you can see part A, they wanted us to find h prime of 6 again. And so there's 1 point for the estimate and 1 point for interpretation with the units. So make sure you write your answer out and make sure you say at time t equals 6 years, it's when it's happening, and it's the rate of change of the height of the tree. The next part wanted us to use, this is where we had to use the mean value theorem. So you had to show the slope, or there was some place where an h prime of t was equal to 2. So we had to show the slope is 2. So you have to show using those 2 points. And then your conclusion using, so because of this, then since it is differentiable, then h is continuous because it's got to be continuous. Then you can use the mean value theorem. So there's 1 point for showing that you use the mean value theorem. And the last, well, this part C, it wanted us to know the average height. So you got 1 point for the trapezoidal sum. That was 1 point for this sum right here. And then 1 point for this approximation. And the last part of this question, remember, always answer the questions in words. Okay, and the last part of this question here is 2 points for taking the derivative because you had to use the chain rule. You got to be very careful about that. We have to use a chain rule. They did a slightly different way than I did it, but it's exactly the same thing. And then you got 1 point for the answer. You notice here you only got 1 out of 3 points if you did not use the chain rule. I'm not sure what they would give you that for, but maybe if you did an approximate derivative correct.